much. So,
Okay,
um,
well, that's
but I
good.
do have some questions I wrote down. Let me just get them.
Yeah, let me also get my screen share going. I have been sick all week, and last night I took my biochem quiz at 2:30 in the morning, and I have been getting up at 5:30 every day for OChem labs. So if my brain is not functioning today, I apologize. Like,
I also got 3 hours of sleep last night, so
nice, perfect. So we are right on par together. I love that.
yeah,
I
no
love that for
problem.
us. So funny.
Yeah, so um one of the questions I have is um so I just was hoping you could clarify, like on page 8, if you go to page 8 in the gap notes of the
Of radicals or
like photo bromination.
yeah, radicals. I think I
Yeah,
just have
so
the
my
summary page. What did it say? Let me see. I didn't really put too much in the notes today because there really not too much going on. It's pretty straight. Well, I say that right. It's pretty straightforward, but not too much material. Not too much material. Anyway, what's your question? Sorry, I'm pulling up my
yeah,
own gap notes.
so like um yeah, so my question is on this page, like there's the reactions with like HBr. And then if you remember from last week, we also studied
Oh, this
reactions
is
with
it. Oh yeah, I knew you were going to ask a question about this specifically because it even says in the book. But wait,
yeah,
didn't we learn that blah blah blah? And I was like, oh, I bet you Jackie's going to ask you a question about this.
yeah, and I just don't understand how you know like if the reaction with like if this reaction is gonna proceed with, like with the radical formation, or if it's going to be like what we did last week. Like how do you know like
Um, okay, so anytime so in this specific, remember how I told you last time? So what you're talking about is like, how do you know if we're gonna do a radical right here? Hang on. Do this over
yeah,
here.
like a radical, or it was like last week
Radical
it was
intermediate
like
or the cation? Is that what you mean?
yeah, exactly. With the like what do you call the hydride shift or whatever?
Yeah, hydrogen or methyl shift.
Yeah.
Bottle opener should be in a drawer there somewhere. Yeah, silverware drawer. Yeah, there's probably one on the can opener too. Sorry about that. Yeah, so okay. So sorry. I got distracted a little bit. Sorry. So you're asking how do you know if there's a different because yes, the hydride shift and the methyl shift. Sorry, I heard that part.
Yeah, so essentially last week we did reactions with HBr as well.
Yes.
And in those instances, like you said, you had like the carbocation, and then
Yeah.
depending on if it was secondary or tertiary, you could do like the hydride shift.
Yeah.
And then in this week, there is the reactions with the like same HBr, but then this week we're doing the radical formation. So I was wondering how you know which variant is going to be the one that the reaction proceeds with.
Got it. Okay. Yes. So anytime you see this, that usually means like that you're dealing with radicals because that's like not light energy, what's it called? Um
I think it is just light energy,
yeah, is it
right?
just like yeah, okay. But I thought there was like a special word for it.
Um,
But anyway, you know what I mean. So if you
yeah.
see that, you know you're gonna do radicals. That's kind of the point of this chapter is to kind of um to see what that radical formation is gonna look like. I'm trying to see if I can find the word. Gosh, I know there's a word for it. Anyway, um, So yes, so that's gonna be your like indicator. But remember we kind of talked a little bit about like the radical stuff as well last week. Remember with like the radicals being on the more substituted, they're more stable, so they're less, you know, uh or like the least stable radicals are not necessarily, they're going to be kind of the easiest ones to make bonds with, all that other stuff. So that's kind of where we're like leading, where with this is to be able to kind of see that, because we're not going to have shifts. That's the thing, like with our cations we have those either hydride shifts versus or methyl shifts, unless it's already on the most substituted carbon it'll be on, right? But
Yeah.
wherever that radical is formed, it's going to stay there. So you're not going to deal with the shifts. So that's kind of the biggest thing here. And then, with like these reaction summaries, again, we're kind of going back to that idea of where if you have this peroxide, you're going to have your anti-Markovnikovs, right? Because where is it? Remember we did that quick and dirty right here. We did the quick and dirty reaction summaries.
Yeah. Yeah, that was really helpful.
Yeah, good. Yeah, so you notice how you don't see any of the, geez, you don't see any of these, right?
Mm-hmm.
What the heck is the freaking word? I was trying to find it. I cannot think right now. Anyway, so you don't have any of that light energy, basically. Actually, I know there's a word for it. Anyway, so that's how you're going to know the difference. So if you see Br2 CCl4 with our inert solvent, or Br2 with our ethyl alcohol, whatever this is called.
Yeah, I see that's the other one I'm confused about, just because like how last week it was simply just like it was like
Anti-Markovnikov?
yeah yeah no wait
Oh,
anti-Markovnikov
anti-addition. I'm
and
sorry, anti-addition. Anti-addition.
yeah
Opposite sides.
yeah that one was just like the wedge and dash thing, right? And then the
Yes.
Markovnikov has to do specifically with the substitute, like how substituted it is.
Substituents. Yeah.
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 So like last week when we were dealing with the diatomic bromine and like we just did the anti-addition, then that's kind of the same question with like the HBr. Then like this week when we had done that, um, where let me pull it up. There were just reactions with diatomic bromine, and then it
This?
was like the radical stabilized.
Oh, from this week. It is just
Yeah.
light energy, by the way. I found it, and it's literally just H nu.
So that's yeah. So like
That's how you'll know
that's
you're
the
going to do the
difference.
radical, yeah. Because it's energy. You're basically putting energy into that bond. So rather than the electrons going and stealing, like here, we have this light energy that's specifically breaking this bond. Just imagine it's like cleaving it in half almost. Versus here, well, let's use a diatomic bromine. Hang on. Right here. Versus like right here, we're gonna have right? And we're gonna have, this. Let me make sure I draw this correctly. Right, which is gonna, make this bond. And break this, right? And then we have, so now we have these electrons that are, and then we have our in between, right? So we have our Br here, and then we have our Br here. And then, but then we have this kind of shift, right? Where it's happening, where we've got this kind of forming at the same time. And then that's how we have this anti-addition, right? We end up having one, because imagine that, our planes, right? Our plane of symmetry, we've got this kind of plane that's going through, right? So that's why these ones, well, that didn't work, but you get what I'm saying. And then this goes over here, so that this is on a different plane than that. And even, you know, that one back there is like going into the paper, right? Imagine what's going into. So anyway, so we have this that, you know, ends up, this BR is kind of here, right? And it's standing between these two bonds. But then when this other BR comes in, you know, then it comes in and it does that kind of backside attack on the other side. And then one bromine picks one side and one bromine picks the other, but they're on different planes of surface, right? So it's kind of just our typical, you know, curved arrow pushing, so they say, right? Versus when we have these H news down here, you're literally like breaking that bond in half. Whoops, what am I doing?
Yeah,
So
but didn't you have to break the bond, the diatomic bromine bond in the example you just showed as well?
So you're breaking it. So just imagine that this, you have two electrons and this light energy here is shattering the bond like this versus we have, that's not what I wanted, a little bit thicker here, versus we have BR. And let's just draw some arbitrary alkene, right? So here we have, let me change my curved arrow color. Here we have, we're taking this, we're breaking this pi bond, right? And we're now creating this bond between these two, but now bromine is overly full. So we're kicking these, both of these electrons we're kicking to bromine. And both of these electrons, I'll use it in a different color, both of these electrons are getting put in this bond here, right? So all we're kind of doing is this bromine here is giving up these two electrons that are now going to come over here. So now let's just say that this is now what it looks like. It's now going to look like this, right? And then there's those two from this bond here, right? And then this over here is going to look like, right? So let's draw this arbitrary, right? And we made the bond here, and well, not what I wanted to do for color, but hopefully you get the point. This bond here is these two, right? And then we've got this bromine with its two electrons. So these electrons, and these electrons didn't go anywhere, right? These two electrons here in this pi bond got transferred to this sigma bond. Does that make sense so far? And then these two bonds here, I mean, electrons here got transferred to this bromine that would have a formal negative charge, right? So you kind of, hopefully the color's not too crazy, but I was trying to make the point about where all these
Yeah,
bonds are going. Okay, cool.
I totally
Versus,
follow. And that
okay,
one's the
cool.
then that's the homolytic dissociation.
Yeah, see, and then so there's two of them, right? Two
Yeah. Uh-huh.
of these single, see what I'm saying?
Uh-huh. Yeah, yeah, I see it.
Okay,
But
cool.
yeah.
So
Uh
that's how we get, so then if you see here, right, that's why when we do these curved arrows, we do these single-headed arrows to show that we're only moving one electron. That's it, right? Versus when we move a bond, we move a pair of electrons in a bond, we do the double-headed arrow, right?
Yeah, no, yeah, I understand the distinction. But one of the thing, yeah, yeah, but like, yeah, but it's good that you explained that because I didn't like remember that fine detail. You know what I mean? Like how they're different. But one
Yeah,
thing on the homolytic one that I had a question on is like,
sure.
yeah, so like just like right in the beginning, I guess this is just a foundational concept that we're supposed to understand. Like when the diatomic bromine gets
What?
homolytically dissociated,
Mm,
you end up with the two like bromine radicals, if
yep,
you will.
yep.
And then in the propagation step, so I'm looking at like page one, like when it first started, the lesson. Um,
Yes, let me see. What page are we on again? Sorry.
like
Uh,
one.
oh, one of radicals. Oh, geez. Okay, yeah,
Like
okay.
photobromination, like number
Yeah.
one.
I didn't put it on here, but yes, I have it here in front of me. I can reference.
So like, so like, one thing I was confused about was, yeah, in the propagation step, only one of the bromine radicals is being used to like react with the well, whatever molecule you're given. In this case, the CH3, CH, whatever, CH, yeah.
This is the propagation step. I have it up here.
Yeah,
Oh,
yeah,
okay. Geez, this
so
is the
like,
propagation step. Okay.
yeah, so I thought I understood that the professor said that like for the termination steps that like aren't likely, she said like the concentration of a bromine radical is going to be really low.
Yeah.
So like the chances of basically just having excess to like stop the process is like unlikely. But
Mhm.
in this propagation step, like I just don't understand where the other bromine radical is going. Like you have diatomic, you break the bond. Now you have two of them, right? But then you're only using one. And so now you've only used one. You go through the propagation step, you form the hydrobromic acid, and you form the radical. And
Mhm.
then it continues on. And then now now another diatomic bromine is being introduced in order to be broken homolytically again to react with that radical to form the final product. And I don't understand why you have to use another diatomic
This final
bromine when
product, you mean? Oh no, this is the initiation. Oh, you mean
so
like
like yeah, like
how we come
literally
back to how we come back to this? Is that what we're talking about?
yeah, so yeah, what you just wrote, do you see how like where it says break 46 kilocalorie per mole? Why
Break
are we having
46.
to
Oh,
break an yeah,
mhm,
like right in the middle of
right
the
here.
page? Yeah.
Mhm.
So like I don't understand why we have to use another diatomic bromine and break it when you would already have an another radical that you didn't use from the step right above when you broke the first diatomic one.
Okay. So think about this. If you had um how do I like this is in a solution of some sort. And so the radical isn't going to sit on a chair. This radical isn't going to go and sit on a chair and say, okay, you, radical A, you go do your interactions. And further on down the line, I know I'll be useful somewhere. So I'm going to wait a minute. And when you're ready for me, let me know. Right.
Yeah.
This other one will get to react with one of these that's somewhere over here. Right. And
But then like what happens to the other one?
this one is reacting to this one here. This one's reacting here. Remember, there's lots of them everywhere. It's when we do chemical moles. Do you remember how many moles of molecules?
Yeah, it's like Avogadro's number. It's like whatever times 10 to the 23rd or whatever.
Do you know how much? That's a lot. It's a lot of molecules, right? So we're looking at this, we're freeze framing. We're freeze framing this whole reaction. And remember, we're doing mechanism right now, which is useful in predicting the products. And it's useful in trying to understand how synthesis happens. But as far as trying to imagine that I have 1 and 2, and now I've used 1 to do X, Y, Z, and now I'm ready for a second one, but I already have 2 here, so why would I even bother even doing this? Why wouldn't I just go and put this in here, right? It's to show that like you're gonna have, this is kind of part of the mechanism, right? It's the same thing with like, remember how you were asking me about the H2SO4, the hydration reaction with H2SO4, and you're like, I don't understand where this H3 came from, or like why, how did you like just get another H2O? And I said, well, remember that you're having this reaction with trillions and trillions of molecules in a beaker, and it's all happening. So like there's just so much around. So now is that to say that like this step will be like, no, excuse me, I need to wait until I find a diatomic bromine to break in order to have my reaction. I can't take you lone pair radical or lone radical, right? I need to find my, I need to break up this relationship in order to proceed. It's just all happening. You know what I'm saying? Like it's all just happening and going on. As far as exactly why, you know, the course is going to tell you that like this is, I want to see you break another diatomic molecule to put in here rather than using one of these other ones here. I can't tell you for sure exactly why that is. I'm just trying to give you an idea on like a grand scheme as to why you would do this instead of just taking this, right? Because at the end of the day, right, you need to have some sort of completion step. And if you just constantly did this for step 1 and this for step 2, you wouldn't have, there wouldn't be, you wouldn't have any product left to eventually, hopefully, like close this whole gap off. Do you know what I'm saying?
Yeah, no, I understand. I was just, yeah, I guess where it came from was just on the fact that on page 2, she made a point of specifically saying that this termination step with the like radical, like this like carbocation, or not cation,
Yeah,
the like
radical.
radical on the carbon and then like the bromine radical is not common. So I guess like that's where it came from. I was like, well, like how
The
would you
bromine
know that?
radical and the radical on the carbon.
Yeah, like
I
on
I don't.
page 2.
You're talking
Anyway,
about this?
yeah, she was just making the point that like she was just like showing termination steps and saying like they're not common. And I was
Oh, I
just
see
like,
this.
how do you
One
know that?
termination step that breaks the chain is this. Although this reaction does form the final product, it is not included as a part of the conventional mechanism because it's not a part of the chain reaction, and it's much less probable than the propagation step that forms the product. The concentration of bromine atoms and propyl radicals are so low that the probability of them colliding, as shown here, is rather low. Most of the product molecules do not form this way. So basically what she's trying to say is that the likelihood of, let me see, do I have that picture on here? Did I put it on here? Is this, let me see, I'm just trying to see. The likelihood of these, no, I don't have it on here. But anyway, but yeah, what she's saying is like this particular radical where the radical is on this center carbon, right? That's what you're talking about? Yeah, so she's basically just saying that the concentration of your radicals being here on the center carbon is going to be so low that the likelihood of them colliding for that to be your um termination step is not going to be very likely, that you're going to see other termination steps over that. She's just trying to make a point that that's not necessarily how excuse me, how the molecules remain.
And like, also, I think I've asked this in the past. You probably answered it already, but I
No
forgot.
worries.
So like this entire like for like a few weeks, like we've been looking at like the stability of like or like a radical, or maybe I don't even know. I kind of getting confused with concepts, but I think it was like the stability of like a radical, if it was like tertiary, is more stable. Or was that the cation?
Okay, wait, let me see.
I'm just like getting confused because
You're all right. I'm gonna bring it back up. Remember,
no, it
this is
is
why
the
I keep my
radical.
notes.
No, it definitely is the radical because when you're drawing energy diagrams, it's like if it's tertiary, it's more stable.
Here you go. This is it. This
But
is why I keep my notes.
I don't understand like why. Like I don't get like what about like tertiary to me, like it just means like okay, you have a bond to like something that's not hydrogen. Like so why is that making it more stable? Like I just intuitively don't have an understanding. And I don't know if that's like beyond the scope of this class, but
No, it's
I
not
just
beyond the scope of this class at all. Okay. I want you to notice first, because it's gonna be I think if I can explain this correctly, it's gonna be kind of similar, right? That our cations, right, and our radicals, when we are talking about increasing stability or decreasing energy, right? Also says it here. But when we're talking about that, I want you to notice that it is going to be the same, right? See?
Mhm.
Okay. I'm drawing this all out so that we can make some comparisons. Okay, so when you can think about a radical as, it's not really, but you can think about a radical as kind of like a formal charge, right?
Mhm.
We want to decrease energy. So if you have a carbon, let me change my color. If you have a carbon, a methyl, right? We've got these hydrogens. Okay. What do I always say about hydrogens?
Yeah, you say like they don't matter or they're not of any consequence.
I mean, they matter. Get it?
Yeah, I get it.
I had to.
That was
Um,
that.
I had to. Um, they matter. No, they matter, right? Right. There are emotional support Pomeranians. They exist. They matter. They help in some ways, but they're not really doing too much, right? Now, oops, the dog came out pretty good. Now, imagine on this side, I'm just gonna do our tertiary, right? Just for this example. So now we have a carbon. Okay, we've got a carbon. All right. Now, imagine that carbon has a lot of friends. I'm trying to make a guy, but that didn't work out well. Or a panted person, I should say. Anyway, imagine that this carbon has all these friends. Right?
Mhm.
Now, if carbon's been having a bad day, carbon has all these friends that can help say, you got this, right? We love you.
Okay.
Right? You know what I'm saying?
Yeah.
Right? You get the
Uh-huh.
point, right?
I get
Okay.
that point.
Yeah. So carbon's going to be more likely to say, you know what? You're right. You got this. I can handle whatever type of, you know, charge radical, right? But I can handle whatever type of BS life throws my way. Let's just call it radical, some sort of charged particle, some right heavy lifting, right? Versus like this carbon that, no offense to the Pomeranian, but like, you're at home by yourself, worried about these exams and the finals, rocking back and forth. Like, oh my God, I can't handle it. Right?
Mhm.
Does this help a little bit?
No, yeah. I understand the rule, but I guess I just don't like.
Bigger? All right, so you want it like how it relates in chemistry. So bigger
Yeah.
atoms, more stability, right? You've got an atom like this that's surrounded with little atoms like this, right? And then you throw a big old fat charge on it, or a very unstable radical, right? And remember that, like, comparatively, right? This is your electron energy, you know? And like, so what are these little hydrogens gonna do? They ain't gonna do just. You know what I'm saying? You know, versus you got, and remember, all R means is some sort of hydrocarbon chain of any amount that you want, right?
Mhm.
So then you've got this carbon of some consequential whatever size, and then you've got, you know, more carbons bonded to it, and then more carbons over here that are bonded to it, and you've got these, let's just say, these electron energies where things are moving around and creating stability. And then now we want to throw this negative radical on there, right?
Wait, so the stability, I just want to make sure I'm understanding. So like the radical is basically increasing the negative charge. So you're saying that you want a larger atom because it has like more protons in the nucleus to balance that? Is that the point?
Well, remember, the nucleus is protons in the nucleus is completely dependent on the atom. But
Yeah,
what you
yeah.
have here is you're sharing, you're creating these bonds, you're sharing these energy fields with these different, um so like, right, so if I throw a random, so carbon wants to have these bonds like this, whatever, right, these four bonds, and I throw on a random radical. Well, if carbon's by itself, there's only so much that, well, you obviously you're gonna have your hydrogen, right? Like, you can't I don't know what just happened. You can't just like have it by itself, right? But I mean, you can, but you get what I'm trying to say, right? Like, so you're gonna have like these like other smaller little, right? But you know, when you've got just the hydrogen, you've got these like kind of little, you're not really, your electrons are still kind of just chilling here, and then you add on this other electron, say, right, or you know, a cation, but you add on this another electron, there's going to be electron repulsion. But if this carbon has its bonds, has its electrons being shared over here and shared over here and shared over here and shared over here, the likelihood that it's four electrons, you know, being in the same area as this radical are way less likely, because you have this pull of these electron, you know, and remember, you've got your electron density is kind of like more here, right, when you're in like these bonds, right? So a lot of it, this mathematical representation, you got to remember that like it's not like things are static, right?
Yeah.
Like we like to draw things as like these just lines and circles and, you know,
Mm-hmm.
well, I think that was O, but this is supposed to be C, but you get what I'm saying. Anyway, right? We like to draw things so they look very static, but remember that this is not static. There's a lot of stuff going on here, and maybe the electron is over here, and maybe the electron's over here, and then maybe it's over here, and then, you know, and so anyway, when you have these bonds, you're kind of like pulling the electrons away. The electrons are busy somewhere else. So it's a lot easier to be able to have a radical, a standing radical. And I'm doing all this and not being clear that like, right, like carbon would be making three bonds and then have a radical. I keep drawing four bonds in a radical, but I want to make that point that like if you had a radical and a carbon, it'd be because you were doing three sigma bonds with the radical. But anyway, but you get what I'm trying to say.
Yeah.
So anyway, so yeah, so just, you know, so carbon's happy with these, four bonded pairs, but you know, imagine this other, let's just put this would be electron, but we're just going to put it over here on just another molecule, right? But so these, and remember that only these ones are carbons, you know, the orange ones are these other R groups, right? And really it's like, you know, R prime, R double prime, whatever. These aren't necessarily all the same ones, but so, excuse me, um, these electrons are busy over here, these electrons are busy over here, these electrons are busy over here. So it's a lot easier for this radical to exist in this space.
Mm-hmm.
Does that
Yeah, no,
help?
I see that. That makes sense. I wasn't thinking of it in those terms, like about, taking into account the sharing and the locations and that I enjoyed like that description. I
Yeah,
wasn't even thinking that.
yeah, good.
Um, another question that I
But it's a
have,
mess. I feel like I'm right up with Dr. Gould at this point. Okay, go ahead. What's your question?
another question that I had, it also kind of on the intuition side, if you don't mind,
Sure.
is like, so for the allylic bromination,
Yeah.
um, yeah, why is it that you're only looking to, um, or why is it that like the reaction proceeds in a way that the bromine is added to the allylic position? Like, I just don't.
Stability,
Yeah, so like why is that more stable?
resonance.
Oh, because the other carbons are sp3.
Mhm.
Is that why? And the other one has the double bond.
Well, resonance has to do with sharing electrons. Remember, we electrons want to be as low in energy as possible. And imagine a lion. Can you tell I like metaphors? Imagine a
I
lion.
can tell.
Because they work well though, honestly.
They do.
Imagine a lion, right? Now imagine a lion in a zoo. Sad lion, right? Versus imagine a lion on the Sahara, free to roam wherever it wants and eat zebra and live its life, right? It's got more space, it's happier. So think of radicals and resonance in the same way, right? Like this radical doesn't have to just live here, it could live here. You know what I'm saying? So now it doesn't just have this space to move in. Now it can move in this whole area, right? It gets to kind of exist in this whole giant area because of resonance. Versus if it was right here, it would be kind of stuck in this area. Right?
Mm-hmm.
Does that make sense?
Yeah, I think, yeah, I see.
It's supposed to be this
And
way,
then, but then on that same page, or still on page 5, like
yeah.
it's exactly the point you were making earlier about it says like, wait a minute, didn't we just add
I know.
diatomic
Yeah, I
bromide
read that. I was like,
or
oh
whatever?
gosh. Yeah, where
Yeah,
is that? It's so funny.
yeah, it's and then that's like kind of circling back. Okay, I guess so then that's
Oops.
circling back to your point is that this is a reaction that is in the presence of this light energy.
Yeah, exactly. Yep, 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 yep. You are right. Where
Okay.
is it? I know it's in here somewhere because I was like, I read it and I laughed out loud. Maybe I didn't put it in here, but anyway, yeah. Um, oh, right here. Wait a minute. Let me see. Page 5. We have page 5 in here. Oh yeah, it's this reaction. Wait, where's the is it? It's the yeah, it's this one. It just says it right before it. I didn't actually put the words in there, but yeah, it just says it before. It says, wait a minute, did we just learn that diatomic bromine adds to a carbon-carbon double bond? And it does, and it's difficult to ensure that the substitution occurs without addition. So this problem can be solved by using a very low concentration of Br2 to minimize addition to the alkene. This requires a new reagent, excuse me, and that's where we start getting into that NBS, which is right here. Oops, NBS. So we'll start doing that. So we'll start adding that so that excuse me, so that you can control your reaction.
Yeah, so and like I know I should know this already, but like I do not because okay, the thing is the last test when we kind of had to like know this stuff,
Yeah.
I don't think I necessarily had the time to gain the intuition. I just know the rules, which isn't the way I like doing it.
Yeah.
So on page 6, if
Yep.
you could maybe like break down so it says yeah, so it's showing the allelic bromination. I don't have a problem with figuring out where the bromine goes. Yeah,
Mhm.
that's like not the issue. Um,
Okay.
the issue is more like because it says the reaction is the substitution of H for Br and proceeds via a resonance stabilized radical intermediate. Therefore, there will be no rearrangements. I
Yes.
don't understand like how do you know that therefore there will be no rearrangements part?
Radicals don't rearrange. Only cations do.
Okay, wait. So when it says rearrangement, is it what is it exactly? It's talking about the like shifting.
Yes, the hydride and methyl shifts.
That's it.
Yep. So if we have this,
So then nothing in this entire lesson should have rearrangement.
right? Yeah, it literally says that. Where does it say that?
Wait, you do know you're muted, right?
Oh my God, when did that happen? That's hilarious.
I don't know, but I was just like,
OMG, you're like, why are you not saying anything? How long have I been muted for? That is too funny.
I don't know, long enough to the point where I was like, I think she doesn't know.
OMG, that is freaking funny. Okay, thank you. But you
I
could hear
was
me a
like,
minute ago, right? I don't understand how that got muted. That was so weird.
I don't know. So I didn't realize because you're like the last thing I heard was you said, it says it somewhere. And so then I
That's
thought
so
you were like looking for it, and then I was like,
And
wait.
then you saw me highlighting stuff and you're like, oh my
Yeah, and
God.
I was like, huh?
Oh, that's hilarious. Okay, yeah, anyway, this is maybe what, so the addition is simple, no rearrangements. Yeah. Anyway, there you go. That's so funny. Oh boy. Here's another right here.
So then wait, so you use a peroxide. That thing that okay. So then the use of the peroxide is a different problem. That is making
Yes.
the
Anti-narcotic coughs.
yeah.
Mm-hmm.
Okay, but okay, wait. So I just want to clarify something. The Markovnikov addition, I understand like, what goes where, but
Mm-hmm.
isn't the whole reason that the atoms go in certain places to make it more stable?
It's to make the intermediate more stable. Remember, that's why the bromine in like our HBr reactions will go to um the most substituted carbon on the alkene because
So then,
that's yeah.
but then, so then,
Excuse me.
then why would you want to force it to be anti-Markovnikov if that's making it less, the intermediate less stable? Like, I just don't understand.
Do you mean like in general? Why would we want to do that?
Yeah, like we're like basically the
Like,
way
how
it
do we
sounds to
apply
me is
this
like,
concept on a large scale, or do you mean like specifically in these mechanisms? That's what I want to know.
yeah, I just mean like in the lab, like why is it advantageous to like
Well, because imagine that you
purposely
want to
force it?
make, well, because think of it this way. Imagine you have this and you want to make, I'm literally making something up. Please do not think that this is real. And you want to make this, right? Let's just say let's just put BR on here for the sake of it, right? Because
Yeah.
that's what we've been doing. Let's say you want to do this. If
Yeah, so
you,
it's not making it like extremely unstable though. That's like that's just what I'm
it's not
getting
going to
at.
blow up.
Well, I don't know. I don't know. I don't know. Like,
No, it's not going to blow
but
up.
it's like saying like
Although
something's
magnesium,
more.
apparently, when the air hits it, it does spontaneously combust. I'm doing the Grignard reagent reaction tomorrow in lab, but so it's very, you got to be very careful. Anyway,
No, like
maybe the
I just
Grignard,
like
but
the thing is like everything is relative, right? So I don't
yeah,
know like
we're not like making atomic bombs here. We're just like because like eventually, what this is all leading you up to. I know you can't see it yet, and you might not be too happy about it when you get there. But what this is leading you up to is synthesis of molecules. To be able to create, to be able to start off with something simple, right? And turn it into, you know, something that's like, blah, 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 crazy. That doesn't even look anything like it. All of a sudden you end up with a molecule that looks like this and this and this and that, and you're like, I don't even see the ring anymore, right? You'll get there. This is kind of like more of an intermediate thing. You wouldn't really see that at the end product, but anyway, you get what I'm saying, right? Like, um you
mhm.
know
Yeah, and there's
so we're
like
leading up to that. You're just
just
learning the
one
simple stuff right now. Yep, I'm listening.
One other thing that is kind of like off topic a little bit, but just that I'm still confused about is so the whole idea of making a bond. Okay, so like if you have an element to say it's carbon, right? And then carbon is bonding with hydrogen in one instance, or carbon is bonding with oxygen in another instance. For example, I still lack the understanding as to like which bond is stronger. There's a statement on the top of page 7, and it's talking about a peroxide. It's saying
Yes.
the oxygen-oxygen sigma bond in a peroxide is weak
Yes.
because the two oxygen atoms are small, which reduces the atomic orbital overlap. So,
Wait,
so
what?
what I take, but then
Small.
I thought,
Wait. Hang on.
yeah,
Reduces the atomic orbital. Wait, show me.
it says the oxygen-oxygen sigma bond in the
Oh, up
peroxide
top. Okay.
is weak because the two oxygen atoms are small, which reduces the atomic orbital overlap. Like that confuses me because
Well, okay, so this really, I'm not sure if reduces is because this really kind of has to do with um, electron repulsion, right? So oxygen doesn't want to be right next to another oxygen because they have those two unbonded lone pairs that are happy to exist. And plus, remember that oxygen is super greedy. And so imagine have you like, think of like, think of like the greediest person right? And imagine two of them in the same room. Like that would not work out very well, right? Like imagine two toddlers fighting over one stick of gum, right? Like that's not gonna end well. So same thing with
mm,
oxygen, not as if it's gonna blow up, but it's just like they both want the exact same thing, and imagine what kind of like disturbance that would cause in that single bond that's like they're bonded to each other, right? So so there's that, and then
yeah,
the fact that there's the electron repulsion of the non-bonded pairs, right? Now, as far as this, the peroxide is also weak because the two oxygen atoms are small, which I understand, which reduces the atomic orbital overlap. So I imagine what that means, and I don't know for sure, but just based on the knowledge that I have thus far, you have these because oxygen is what, 8, right, or 16, sorry. um so you have these kind of smaller oxygens, and remember you want to have some sort of overlap to create that. You have to have that overlap to create the bond, right? So you've got to
I just have
have.
a question on that point though.
Yes, I'm getting
Oh
there.
wait,
I'm going to show you.
is
I'm getting there.
oh, okay,
Just give me a
okay,
minute. I'm getting there.
okay.
Right? And so these bonds can only, they can only go so far, but what you're really gonna have, remember, is you've got these lone pairs of electrons, both of them, and they don't want to be friends at all. They're gonna be over here like, get out of my space, right? While these kind of, because these our sigma bonds have to get kind of close to each other in order to create this. That's what they're kind of talking about. The atomic overlap gets small because no matter how hard you try, this ain't coming together, right? So that you're going to end up having these oxygens because of these lone pairs of electrons. Let's just draw these really big electron density clouds. If these are it, but then our sigma bonds are like, right? Like you just got this little tiny. What is going on? You just got this little tiny overlap right here, right? Versus like carbons, let's just say, or even nitrogens are close by, but let's just use carbons because that's only 4 AMUs off. That's not a whole lot, right? So you've got these carbons, but they don't really have any, they don't have that electron repulsion. So even though maybe their sigma bonds are, um, you know, comparable in size, they've got a lot more, and they're also smaller. They've got a lot more overlap because they don't have these giant electron clouds that are repulsing each other. So that's what I would imagine would be the reasoning behind it. But I am not, I don't have my degree in chemistry, so I can't confirm that.
Yeah, I just want to ask maybe this is just, I just want something clarified from like week one
Yeah.
with an orbital.
Yes.
Isn't an orbital just a probability though?
Yes, it is.
Like an orbital isn't even a thing. So when it says like you want atomic orbital overlap, I struggle to understand like what physically that means because I'm not under the impression that an orbital is a real.
I mean, it is. It's energy. It's a real thing. We have the bonds. We've got the power. We've got the
Is
proof,
it
right?
wait, but
Like,
is it when you just say like you want atomic orbital overlap, does that just mean that essentially the like you want like probability clouds to overlap so that like the electrons would in theory be in like a similar location to make a bond? Like that's what it's
yes,
trying to get at?
yes, yes,
Okay.
yes, ma'am. So you remember this stuff from week one,
Yeah.
right? So we have these atomic orbitals here that will make molecular orbitals here. Remember, we've got our bonding and our anti-bonding, right?
Yeah.
Bonding and anti-bonding, right? And so that's when we have these the lineups, right? Our nodes are all in the right spot. So that's this um in phase overlap here. So this is in this picture is atomic orbitals, and this one would be your molecular orbitals, because remember we kind of just blend them together,
Hmm. Yeah.
right?
Yeah.
So it's that same thing. So this was what I was trying to talk about with the sigma bonds, right? The sp2 or the sp3s, right? So this is what I was trying to talk about. So we have this atomic overlap here, but now imagine the same thing, but like, obviously I'm hoping that you can understand my thing here, but now imagine that, we've got this atomic orbital here, and we've got this atomic orbital here, right? And let's just say these are our O's. I'm gonna put O's over them. These are our O's. And remember, compared to protons, or like electrons are tiny, but they require much more space, right? And so if you've got these two sets each of non-bonded, right, electrons, they're trying to repulse each other, right? Because they're happy existing in their own space, and this is like a totally two-dimensional thing, right? And then you've got this electron here that's hoping that it somehow finds this electron over here, but meanwhile you've got all this noise. You've got all this noise that's preventing these two from ever finding each other, or maybe just barely finding each other, right? Because as far as molecules are concerned, distance does not make the heart grow fonder. It makes the bonds weaker.
Mhm.
So that would be why, like, yes, oxygen are smaller. And so typically what we say is that smaller molecules have greater overlap because they're able to come together more, right? But they're able to come together more typically because they're smaller. They don't have as big of an electron density cloud, right? Whereas those bigger molecules, like say, bromine or chlorine or something like that, they're these huge molecules. Well, this is how big this molecule is compared to, say, this molecule over here that's a quarter of the size. Imagine how big this electron density cloud is for this molecule, right? It's enormous. So this is never going to be able to get close enough because this electron density cloud is happy little electrons that are bouncing around that don't want anything to do with any other electrons going on, right? For this giant molecule over here, right? And then we've got this other one. So this other one's got this one, little electron that's like, hey, let's share, right? But in the
Mhm.
meantime, these other ones are like, dude, I don't need to share. I've got all my stuff going on. So that's why we say that like this bond is weaker when it's to a larger atom because it's less of an overlap. And these atoms can't get close enough together because the electron density cloud is too large in comparison to these smaller diameter atoms.
Yeah, so
Right?
like the statement about the oxygen, it's relative because they're saying it's weak because there's not a lot of overlap, but like at the same time, like there kind of is because they're like compatible in size. I don't know, so they can get close enough to each other. I don't know. Like
No, they can't, but that's the
they
point.
can. No, but they can though, right? Because like they're not like a bromine atom where there's like
Negative. That's why I was trying to explain to you. That's why, look. Yes, they are small. This is why it sounds a little counterintuitive, right? So, yes, typically smaller atoms can get closer together because their electron density clouds aren't overtaking. But remember that, say we have these two carbons that have these 4 electrons that want to make bonds, right? These guys can get together because they want to share. They don't have enough, so they want to share, right? But now let's compare that to oxygen's not that much bigger. Like we're not talking about that much bigger, right? Just a little bit. What did I say? 6 AMUs or something? 4 AMUs, not even, right? 4 AMUs. And oxygen's got these, that are like, hey man, let's get in a bond, right? Little brothers, right? But oxygen also has these wicked happy big brothers that are like, nah, I'm good. And this one's like, nah, I'm good, right? And I'm drawing this on a 2D scale. But because of this electron repulsion here, this is going to kind of take precedence over this hopeful atomic orbit or molecular orbital, right?
yeah.
Why would it try to do this when it could just as easily and happily come in with a carbon who does not have that type? What color did I do carbons? Blue. Who does not have all this electron noise, right? This is a lot of electron noise going on right here, right? So this does not have, this other carbon does not have all this electron noise. And this other carbon's like, hey man, you can totally share my carbons. I'm down. And then I'm also just going to share it with this other carbon over here and this other carbon over here, right? Way less noisy, way more civil relationship. So that's why this one's like a weaker bond because you've got that electron repulsion.
Okay.
Hopefully
But yeah,
that
that
helps
no, that
conceptualize a bit.
that does that makes sense.
Cool.
Also,
Yeah.
um, if you don't mind, can you go to page 8 again
Yeah.
of the same lesson?
Yes. And in about 15 minutes, just FYI, I do have
Yeah.
to be a little bit more diligent on my time this week, but
Yeah,
um
sorry.
no, you're fine. I'm giving you just a heads up. All
Yeah,
right,
yeah.
page 8. It's like this area, right? Maybe.
Um,
Let's see, what's in
it's the
okay.
ones with
Oh,
the
I'm not far enough down. Or I'm not far enough back. Sorry, that's all chirality. You're probably not there yet. Okay, it's
yeah,
this
it's
stuff up
that. It's
here.
there right
Yeah.
there. I was wondering if you could just explain the difference between these two examples to me and then also explain. I'm still just like not clear on the regio specific and stereo specific and then
I
how you
know,
know
right?
the like top and bottom backside stuff. Yeah, I don't get that whole thing.
Yeah. Yeah. So backside attack is going to be when you have something like not in the plane. So remember how bromine can where's our other one where it's like bromine kind of came in? Oh, like this, right? This one right here. How when you have
Yeah.
so this is from last week
Mm-hmm.
because we didn't see how we added two versus just adding one, the substitution versus like adding like this addition reaction, right? So substitution is because of this reaction, right? Where we have this just radical going on here versus this
Yeah.
addition is when we had the, I think it was just BR2, right? And was it MBS or something? Or not MBS. Um, is it just BR2? Thought there was some sort
That
of catalyst with it,
one
but
is wait,
oh,
the
yeah,
NBS one I thought was when you only add one.
yes. No, I know. I didn't need to say MBS because that's right there. Where's the reaction summary? It's right here. Oh, CCl4. That's what it was. I know it was something. I couldn't remember what the catalyst was. I'm like, is it SO2 or or SO4, H2SO4, BR2 and CCl4. Right. So anyway, this is just your inert solvent, not the two, but you get what I'm saying. CCl4 is just the inert solvent to help it move along. So anyway, what happens in this one is we have, what is this, a pentose or a pentanous by biochemistry. Right. And so we have this, we break this bond here and it comes over, we electron to bromine and we make this bond here. But then, we also have this here. So we are going back and forth with making this. So anyway, so bromine's on this side. So then we have that other bromine. Because remember this imagine like the corner of your desk, right? Being like this positive charge or like the corner of your book, right? But if you have like something on top of your desk that's getting in the way, you might reach from underneath in order to like get to that space, right? And so that's why you would have these anti-addition because bromine is a pretty big molecule, right? What's bromine?
Yeah, I do
79.
I
Yeah.
do understand why you would have anti-addition to reduce electron repulsion,
Yeah.
but for the picture you're drawing on the right-hand side, I don't know, like, how do you know if like the bromine bond is like above or below the plane? Because that changes if it's like attacking from a top or bottom.
It's both. Or my phone. No, okay, you can still hear me. Okay. My headphones are gonna die soon. I gotta charge them tonight. I think I said that last time. Then you have plus minus, right? So you have so remember this is all relative, right? So you got a bromine on this side that's making this bond, and then you get this is the front side, but then imagine that, bromine's on the back, you have both of these happening at the same time. And so that's why you'll get to later in this chapter. Eventually, right now you have to write plus, whoops, not the parentheses, plus this, right? Right now. But eventually what's going to happen is you're going to get to the point where you get to do this. And that's just basically saying that you have both. Right. So that's what we'll get to. But so you're going to have both. You're not going to have, oh, this bromine's always going to attack this on the front side because this V has an extra little curve on the tail there. And that's how I figured that out. No, it's happening on both sides, right? So you're always going to have that. But now we're talking about, so this is where that BR2 adds to the carbon-carbon double bonds. But right now, what we're talking about when we're talking about H nu is we're talking about creating radicals. And so when you create a radical, the reason why you're having your bromine on this random other atom, as opposed to on these nice, beautiful substituted, right, carbons, like we do here, is because we're not breaking the alkene. What we're doing is we are putting a radical on the most stable carbon because we're breaking a hydrogen. What we're doing is we have this right? We've got a hydrogen here, and 2 here, and 2 here, right? And so what's the most stable place for a radical to sit? Equally stable, because they're
Mhm.
allylic, right?
Yeah.
So then when we have our Br2, oops, well, whatever, you get what I'm saying. When we have our Br2, we apply our light energy. Right? Oops, no, it's just regular H and then, okay. We apply our light energy. What happens is this goes this way, this goes this way. Oops, what am I doing? Oh boy. This goes this way, this goes this way. Oh no, wait, yeah, no, I had that right. Boy, I don't know what I'm doing anymore. Oh my gosh. Oh God, you get what I'm trying to say.
I get it though.
Yeah, I know, I'm sorry. It's just like, it's not my day. Anyway, so then you end up having this. My point is, geez Louise. My point is that you have this radical sitting here. And then you have a bromine, right? I'm supposed to break this off is what I'm supposed to do. That goes there, that goes there, that goes there, that goes there. There we go. Geez Louise. And then we have the hydrogen here. We have the hydrogen here and the 2 bromines, the times 2. Gosh. Whew. It's a rough one. So anyway, so once you got that, right, then that's when you make your bond, right? Whoops. But we kept this alkene, right? And these 2 are the most stable because they're allylic, and we decided that that was one of the highest stability places that I could be. So right now what we're looking at is to say not where is the most stable place for the bromine to go, which is why we put it on a most substituted carbon. In this case, these were both equally substituted, right? But now we want to say where is our radical the most stable? And that's where we want to break the bond. We want to break the bond where our radical will be the most stable, so that then we can have our radical bromine come in and make a bond to it. And that's how we end up with this.
Mhm.
Okay. So right here, resonance. And then we just add the bond. We had the bromine wherever we could have easily have added it here in your drawing. It doesn't matter as long as you're following all your stuff, right?
Yeah.
What was the
Yeah,
other
so
question you had? Yeah.
yeah, so it was like looking at page 8.
Yes.
If you could like explain the difference between these 2.
Oh yes, thank you. I knew there was a question. What did I do with it? Is it this? That's this.
And then
This. These ones.
yeah.
Okay. So compare the conventional Lewis acid base reaction of the alkene HBr to the radical reaction that is initiated in the presence of peroxide. Okay, so in our HBr, no peroxide versus peroxide. Radical intermediate, no changes, and then this is the cation. So these are okay, I get it. This is the product, and they're showing the intermediates. That's what they're trying to say. So the difference here, right, is we have when we just HBr, no peroxide, right? What happens is we're breaking this bond here. So we have a choice. Well, we don't really have a choice, actually. Unless we don't have a choice. There we go. I mean, we do, but it's not, it wouldn't actually, you wouldn't have a cation here is what I was trying to get at. Anyway, hopefully you know that by now. So what we have is, here is the bond that we broke, and we've added the hydrogen to the
Yeah.
least substituted side. Yep.
Yeah, Yeah, then that
So
one's the Markovnikov.
yep, yep. And so
Uh,
then here, so now that's where our bond was, and now we have this cation right here, but then we have the methyl shift, right? So this is all stuff that we've seen before,
yeah,
right?
so I just don't understand the regio-specific thing again. Like I just don't even understand what that means.
The BR adds to the least substituted end. The presence of the peroxide makes the radical reaction much faster than the Lewis acid base. So the reaction is regio-specific because the bromine adds to the least substituted end of the carbon-carbon double bond, anti-Markovnikov. The reason why this does this is so that the radical is the most stable. The radical would not be stable over here. The radical would not be stable if it was at the end here.
Yeah, so what does regio-specific mean
Means
exactly?
that regio-specific means that it has to react in that area. It looks for that area. Let me give you the exact definition of it, but specific. So a chemical reaction in which one structural isomer is produced exclusively when other isomers are also theoretically possible. So it's theoretically possible that we could put a radical here, but that won't happen because that is so unstable. It's literally not even going to happen. It's just not like you might, it just like is just basically just consider it never to happen, right? So that means that it's regio-specific, as in like the only option, because the other one is just not even going to happen. The only option is to put the radical there on the most substituted carbon because we have to stabilize the radical. So that's what regio-specific means.
And
Okay.
then in the other one is not stereo specific. And can you just explain so that is the thing about the backside or front side or top side attack?
This one's not regio-specific because there's no like, I mean, okay. This one's obviously the most stable because it's allylic, right? But this one also could happen because it's not like it just wouldn't be, it'd be like the minor, be your minor product. But let's see, the reaction is not because the addition of H to an intermediate carbon-centered radical can occur either from on top or bottom equally, which means that HBr will add both syn and anti.
How
So
do
if
they
this
know that?
because it's planar.
How do you know that?
Well, in a very simple way of saying this, do you see any wedges or dashes? Oh, I guess this would be a wedge or a dash. This would be. But we're not. These are all sp2 carbon atoms. So these are all planar. The only one that's sp3 is these ones.
Okay.
So those are all planar. So that's why it can attack from the top or the bottom.
Okay. Okay. Thank you for going over that.
Yeah, you're welcome. I'm trying to see if there's anything. If cis-trans isomers can form, then they will. Yeah. Yeah. I would say look for, the biggest thing is try to find where your most stable reaction is going to be, like your stream radical will be, and then if you're not sure if it can go from top or bottom, look to see if there's look to see what the carbons are, what their hybridization is, and if they're sp2 or sp, then they can attack from the top or the bottom. But you'll see, have we gotten there yet where you do the backside attack? I think that's substitution. I think maybe that's next chapter, but anyway, where you'll have, because yeah, we're learning about chirality right now, so you'll see that next. But where you'll have, say there's a BR here, and we break this bond, what happens is all of these kind of shift forward for whatever it is that you're putting on, right? Your oxygen or whatever. So your oxygen will come and attack from this side because the bonds are being broken and made at the same time. So you can't make and break a bond in the same area because again of that electron repulsion stuff going on. right? So what you see is on the front side, you're breaking this bond, and on the back side, you're making this bond. So you see these guys kind of shift forward. So that's what chirality is setting you up for. So you can just see more reactions and see how they work, kind of real world style.
Okay. Thank you, Sarah, for
You're
all of the many
welcome.
explanations.
No problem. My beautiful drawings. Yeah, let me know if you come up with anything else that you want to know. But I'll be on here tomorrow too. So I think I said tomorrow, didn't I? It's Friday, I think. But yeah, so I'll be on here tomorrow if you need more help. And then it's the final, you know? So